Thank you very much for giving me the opportunity to talk to you all today. Thank you everyone for coming. It's an absolute pleasure to be here. So as Catherine said, I'm Ben. I'm a PhD student at the University of Bristol, and yeah, if you didn't know, we spy on volcanoes, and that's what I do in my PhD. So I'm just going to uh, talk to you today about why we would want to spy on volcanoes and basically everything you'd ever want to know about it. So I decided to start this talk just with a bit about me and how I really got to where I am. So at school, I was a lover of geography and physical science, and especially the connection between physical science and nature, how the world works. So naturally, that led me to university, to background in earth sciences, and I was particularly interested in natural hazards, which then led to um, a degree in volcanology, so the study of volcanoes. I was then a scientific advisor briefly for a geotourism company. But it was during that time I realized I really want to do some more research, learn a bit more about volcanoes. So then I began my PhD 2 years ago at Bristol University in volcano remote sensing, which is the more professional way of saying spying on volcanoes from space. And um, and outside of science, because it may not seem like it, but scientists do enjoy other things than science. I am a keen mountain biker, which is evidenced by the picture in the bottom right there. Um, but that's enough about me. So what am I going to talk about today? Um, so spying on volcanoes from space. I'm going to answer a few key questions about this, which is firstly, why would we want to do it? Secondly, how do we do it? Three, since when have we been able to do it? And finally, I'm going to talk a bit about what we can see. I'm going to draw on some case studies from my own research here, and finally think about how it might evolve into the future. So, first of all, why do we want to spy on volcanoes from space? And to understand this, we need to think about how volcanoes are monitored and what's useful to us as volcano scientists. Um, when we're monitoring volcanoes. So you can use a whole host of different techniques to monitor volcanoes. You can collect a whole different load of measurements, uh, basically to better understand how they work and hopefully be able to better forecast future eruptions. And you can see with this graphic on the right that just gives a nice schematic of a few of the different techniques we can use. And there's about four measurements that we are most interested in that can tell us the most about what a volcano is doing. That's firstly, there's gas emissions. So there's sulfur dioxide, carbon dioxide, water vapor, and helium are some really important gases that can tell us what a volcano is up to. Thermal emissions. So basically where on the volcano is hot and how hot is that can be really useful to us. Ground deformation. So between eruptions and also as a volcano is erupting, the ground around it might either inflate or deflate, and we can measure that. That can tell us what's going on beneath the volcano. And similarly, earthquakes. A lot of volcanic activity is associated with earthquakes. So by measuring where they happen, how deep and how strong they are, we can get an idea of what might be happening under the ground. And traditionally, these have all been measured by instruments situated either on or around the volcano, and we can measure them all that way. Uh, so you might ask, well, if we can measure all of these different things from the ground, why do we want to monitor volcanoes from space then? And there's a few really good reasons why we might prefer to do this uh, over monitoring things on the ground. And the first is accessibility. So as you can probably imagine, volcanoes are often in hard to get to inaccessible places, in inhospitable conditions. I picked just about the best image I think I could to represent this. These are some Italian volcanologists from the 1930s, and the lengths they went to get some of their measurements. So you've got some rudimentary heat suits on the left, and on the right here you've got a guy literally rappelling into a volcanic crater, I think to measure some gases, maybe. Um, and that brings us on to the second reason, which is reliability. So in these inhospitable conditions, especially when a volcano is erupting, you put down a piece of electrical equipment to take some measurements. That's not going to last very long a lot of the time. Um, and third, this might surprise you, but actually the cost. So uh, monitoring things from space is quite expensive, but actually, um, when you consider that there's about 1,300 active volcanoes on Earth, sometimes very closely spaced together. Um, and you have to put suites and suites of equipment on each volcano to properly monitor them from the ground. That very quickly gets very, very expensive. Um, Similarly, data coverage. Um, so obviously we can only monitor as many volcanoes as we have instruments on the ground for. Whereas if you're monitoring them from space, you can image the whole world basically in any volcano you want once you've got the infrastructure up there. Um, and finally, flexibility. So if I got a call from authorities, I don't know, in some country in Africa saying there's a volcano that they think might be doing something, but there's no monitoring, uh, no instruments on the volcano. It could be weeks or months before an exhibition could get out there to install some equipment and see what's happening. Whereas we can simply um, make a call to people operating satellites, and they can maneuver and probably get an image of that volcano within a few days. So that's really the why of how we monitor volcanoes from space. So how do we actually do it? So I've kind of alluded to this already, but we monitor them using a whole different range of satellites. Um, and how this works is that all satellites on them have sensors that detect electromagnetic radiation, um, similar to the way a camera works, and they detect electromagnetic radiation along the full spectrum of wavelengths from um, generally, as you can see on the right, generally the satellites that we're interested in for volcano monitoring are either in the microwave band, infrared band, the visible light band, or ultraviolet light. And basically every satellite sensor is sensitive to a sort of small window within that range. And out of our four volcano monitoring data sets that we mentioned earlier, um, satellites can do a really good job of measuring gas emissions from space. They can do a really good job of measuring thermal emissions, so where's hot on the volcano. They can do a really good job of measuring ground deformation, so if the ground's inflating or deflating over time. And the only thing they really struggle on is detecting earthquakes from space. So we are really good at detecting really big tectonic earthquakes from space because they deform the ground quite a bit. We can detect them that way, but generally the earthquakes at volcanoes that we're interested in are much smaller, so we struggle to detect those. But the other three we can do a really good job of. Um, so for the next part, I thought I'd just give a background, a bit more of a background onto the different types of satellites we use and what they look like. So on the top right there, you've got a satellite, which depending on your perspective might look really small or really large compared to how big you thought a satellite was. And yeah, so satellites are launched into space on top of rockets, and generally the ones used for science maybe have a life of maybe 5 to 10 years, maybe more, So they're constantly being replaced with some new and better missions. And the satellite sensors that I was mentioning earlier, they can be split into two main types of sensors, called active and passive, or they can also be called radar or optical. And basically, the passive sensors just means that the sensors passively detect light from the Earth. So light that's just being naturally reflected up from the Earth is detected by the sensor, or sunlight that's been reflected off the surfaces you can see in the bottom left. And active sensors is different in that active sensors actually fire a beam of light directly at the Earth from the satellite, and then they measure that light when it returns to the satellite, and that can tell them a bit about the ground surface. Um, so going more into detail on passive and active satellites. So passive or optical satellites, they only, as I said, they only detect radiation admittedly passively from Earth. Um, they're really good for measuring land surface properties. So, for example, the temperature of land as well as different chemicals. So, volcanic gases, in our case, and these and the sensors on these satellites generally fall within the ultraviolet, the visible, or the infrared um, part of the electromagnetic spectrum. And you can see on this top right figure just a few of the kind of things that can be detected at different wavelengths. So vegetation, soil, water, um, things like this. Um, and generally a satellite with an optical sensor will measure a wide range of these different things. And you can see in the bottom right an example of an optical image from a passive satellite, and you can see that it very much looks like it's very much probably what you're used to seeing in terms of satellite imagery of the Earth. It very much looks like a photograph. Um, you could also put using the infrared ultraviolet, put it in false color to highlight maybe the vegetation or some other properties, but generally they're kind of quite easy to interpret. And then moving on to active or radar satellites. So like I said before, these emit a pulse of low frequency electromagnetic radiation, and then measure these pulses as they return to the sensor. And these are generally much longer wavelengths. Um, these emit microwaves or radio waves, and these are really useful for understanding ground surface characteristics. So, for example, ground inflation or deflation. And in the bottom right there, I've put just a couple of examples of the types of imagery we get from these satellites. As you can see, they probably look a bit strange. They're definitely um, not as intuitive as the optical images, and I'll come back to explaining how we interpret these sort of images uh, later on in the talk. Um, but yeah, they're really good. As I said, they're really good for measuring ground inflation and deflation. Uh, so those are the different types of satellites that we use. And before moving on to what we can actually see from satellites, I thought it'd be good to just give a quick overview of, I guess, of the history. So since when were we able to monitor volcanoes from space? We haven't always been able to do that. So I guess the first pioneering work began in the 1960s, trying to detect thermal anomalies from volcanoes from space, but it wasn't really until the 1980s where it gained traction. So these two images on the right are some of the first two um, detected thermal anomalies, volcano Lascar in Chile, and then at Mount Erebus in Antarctica. Uh, but this was very much still a field in its infancy. There really weren't many images available at all, and any processing or analysis of these images, any techniques were basically yet to be developed. Um, and then we move on to the 1980s. Again, like the 1980s was very much the start of when gas measurements started to be taken of volcanoes and ash clouds as well. Um, and the biggest focus of these measurements was on the detection of ash and sulfur dioxide, which is kind of still true today in these fields. So this image on the right, this is from one of the earliest examples of this. So this is a map of basically Central America. You can see Florida up in the top right in the Gulf of Mexico. Um, and just below it, if you can see my cursor, you can see El Chichon, which is a volcano in Mexico, which has erupted. Um, and then these these outlines here are basically mapping where the ash and gas cloud from this volcano has traveled um, throughout the days after it has erupted. And yeah, and like I say, this was basically the start of measuring gas emissions and transports from cloud emitted by the volcano. And these were all, I should say, these were all with passive or optical sensors. And then we move on to the 1990s, which is when active sensor satellites start to be used for monitoring volcanoes, and this is in the form of ground deformation measurements. Um, so if you look at this diagram in the top right, this shows kind of how this works. So basically, as the radar satellite passes over the ground and emits a pulse of light, it basically measures the distance between it and the ground. And then if it comes over a second time at a later date and the ground is inflated, that time will be shorter. That distance, sorry, will be shorter. And therefore, you're able to extract how much deformation there's been. So the technique for doing this is a bit of a tongue twister. This is interferometric synthetic aperture radar, or INSAR, which I'll refer to more later in the talk, as we use for detecting ground motion at volcanoes. And this produces these rather amazing psychedelic-like images that you see at the bottom. Um, so this is a satellite image of a volcano called Okmok in Alaska. And basically how you interpret these is where you see these colored fringes. So the color as you go from the outside of the image inwards, the colors go from red, then black to blue, and then back to red again. So each one of those red to red cycles is one fringe, and basically the more colored fringes you have between the edge of the image and the middle, the more ground deformation you see. And these measurements are really interesting because they told us that as well as during an eruption, in between eruption, volcanoes that hadn't, erupted for tens or maybe even hundreds of years were actively deforming and moving the ground around them, which we hadn't quite realized before. Um, and then moving on to the 2000s, and here we have the what's called the Shuttle Radar Topography Mission. And this was really a game breaker. This was a radar sensor that was mounted onto one of the space shuttles. This was a special mission which aimed at basically getting a global data set of elevation of ground height measurements around the globe, and it was the first mission to do this globally. So it created what's called the Digital Elevation Model, or DEM. I'll refer to these later on in the talk as well. And yeah, DEMs are really critical for basically monitoring how the topography at a volcano changes through time. And also, um, if we're looking to simulate lava flows or simulate other volcanic flows and where they might go, we need the best DEM possible, the best topography possible to be able to do that accurately. And then once we got into the 2010s and 2020s, so the more recently, um, we kind of had all these techniques, and there's been a big push about getting these data in near real time, and towards automation, because um, before using satellite data was very much something you did after an event, or that took you maybe weeks or months to kind of process the imagery and get a nice looking result out of. Whereas this was when we started to be able to apply it almost operationally during a disaster. So these two images on the top here, these are images taken 2 weeks apart of Mount Merapi in Indonesia from 2010. And you should be able to see just at the end of this arrow here, um, between the two images, there is this kind of black blob that's appeared. So this was actually kind of what's called a lava dome. So big, sticky, uh, kind of bulbous, massive magma that's very slowly erupted from the top of the volcano. And these two images, actually, especially the second one, were very critical in 2010, um, during a volcanic crisis there. And it was actually one of these images that partially prompted some evacuations there, which ended up saving quite a lot of lives when Merapi exploded later on in 2010. And then, yeah, so like I say, using that imagery during crisis for decision making, this was really when that started to be used. And then, secondly, automation. There's been a recent push, um, and this is basically using artificial intelligence to detect when you've got unrest at a volcano. And this is a product of us having way more data than we ever did before, and way more images than we could ever go through manually. Um, so you can see on the bottom left here, this is one of these INSAR images that I showed you in the previous slide. And then this is on the right, you've got a prediction from AI as to where there is deformation in this image. And as you can see, it's doing a pretty good job of telling us that it's right in the middle of the image. So I guess a really important point to make with this, to show the impact of monitoring volcanoes from space, is that since we were able to do this, the number of volcanoes with known activity has increased exponentially, as you can see from this graph. And it's important to note because sometimes um, it may seem like there's more and more volcanoes erupting, and certainly some people choose to believe that, but this is purely because we've just got a much increased number of observations, particularly from satellite data, compared to what we had, 20, 30, 50 years ago. So then for this next part of the talk, I'm going to tell you a bit about what volcanic features we can monitor using satellites. Basically, what can we see? And I split this up to what we can see kind of before and in between eruption, and what we can see during an eruption, and what we see straight after an eruption, or what we can monitor. So I'm going to go through each of these pictures individually. So before an eruption, we can measure thermal anomalies at volcanoes. So, for example, lots of volcanoes have things called fumaroles on them, which are basically just vents that emit hot gases out of a volcano. You can basically detect these. This is this blurry image in the top here. You can't really see that much from it, but just trust me when I say that that's what's been detected there. Secondly, this is moving on to the image in the top right, you've got lahars, lahars are basically mud flows. Lahars is an Indonesian word for rain-triggered mud flows that often happen on volcanoes, where you've got lots of loose volcanic ash that can easily be mobilized in heavy rainfall. And if you have a good idea of what the topography of the volcano is, Um, you can basically simulate how these flows may travel down the flanks of the volcano, and then you can think about which, if there's any inhabited areas that may be at certain risk um, being inundated. So that's what you can see. So that's what you can see here in the top right. You've got obviously the volcano in the middle, and then these blue things are uh, the predicted path of where these lahars are going to flow. And lastly, in the bottom here, as I mentioned, you can use deformation. You can look at deformation of volcanoes, of the ground around them, um, between eruptions. So this is down the bottom here. This is a satellite image from Iceland where there's been all the recent eruptions. So this was an image taken over 2 weeks um, between some of the eruptions that have been happening there. And you can see this scale at the bottom is in millimeters. So you can see that a lot that across those 2 weeks, the ground has inflated there by around about 5 centimeters. Um, which yeah is quite interesting. Um, so moving on to what we can see during an eruption. Um, so the first big one, which is the image in the top left, which I'm sorry has been cut off slightly, is um, is ash and gas clouds. So this is a very famous ash and gas cloud here, or a sort of picture of it. The Eyjafjallajökull eruption in 2010, which famously grounded Europe's airspace to a halt in Iceland. So this is just a map of basically the concentrations of ash and where they're found. And incidentally, since that eruption in 2010, the Met Office in the UK has invested heavily in these sorts of uh, simulations to understand where ash goes once it's been ejected into the atmosphere. Um, and secondly, you can look at vegetation destruction and recovery. So obviously, volcanic eruptions can be very destructive. Lava flows, ash can destroy lots of vegetation, and you can measure the change of vegetation associated with these eruptions. So this is in the top right here. Basically, everywhere you've got green is where you've got thick vegetation. You've got the volcano in the middle here, and everywhere you've got brown is bare vegetation. And what's happened here is during the eruption, a lot of the ash has been blown basically from the bottom left to the top right of the picture. So in that direction, away from the volcano, to the northeast. And that's why you have this big brown area here. This is where all the ash is deposited. And finally, we can look at, as I mentioned earlier, we can look at lava flows and also pyroclastic flows, which are another volcanic hazard, and where they might impact. So this at the bottom is a map from a volcano in Chile, which is the top of the volcano is up here, and basically using some topography of the volcano that we've got from satellite data, we can simulate where these, in this case, pyroclastic flows may flow down the volcano. The areas in red are where it's more likely to flow. And again, we can use this to look at where these are in relation to inhabited areas and think about evacuations and hazard levels and things like that, which are really important. Um, and then finally, after an eruption, so actually a big thing after an eruption, especially one which is affected inhabited areas, is damage assessment. So getting a really good handle on what's been destroyed, what the likely bill is going to be. So for that, again, we can use satellite images, either optical images, or we can use radar images to basically that help us detect where roofs might have collapsed, from the weight of ash on top of them, or various things like that. And we can use that. And this is the image at the top here, to produce a map of inferred damage, like we can see um, on the top right there, with these different colours denoting, I think, different types of building, and then we can ascribe different levels of damage to them and use that to estimate the financial cost of an eruption. And then secondly, we can look at the cooling of volcanoes, which may sound weird to say. Obviously, volcanoes are associated with being very hot, but similar to a lot of things, really. As lava comes out of a volcano, it's very hot, and then as it cools, over time, it shrinks and it contracts, and that's the same with magma chambers beneath the surface. And um, you can measure basically the ground deflation associated with that. So this top right image here, where you've got this arrow here, is basically the top of a volcano, and this red area here is, I think it was a big pyroclastic flow deposit, which was very hot when it was in place, and this was, say, over a few months afterwards, um, where it's basically shrunk, and we can measure that change using satellites. And finally, the big one is changes in topography. So obviously, the classic feature that volcanic eruptions make is a big, huge craters, where material's been exploded out, and we can measure these by comparing the topography of a volcano before and then after an eruption. So this is a famous example from the large eruption that happened in Tonga a couple of years ago, if you remember. Um, and this data set basically showed this volcano, which was just below the sea surface, had basically excavated about a 700-meter deep crater after its cataclysmic eruption there. So that's just an overview of the kinds of things we can measure and monitor, and what volcanic features we can see. I'm just going to end with a couple of case studies, just based on some of my own research here. So the first one of these is looking at pyroclastic flow hazards at Volcán de Fuego. So Volcán de Fuego is a really large stratovolcano in Guatemala. There's about 60,000 people living on the flanks, and it can have large eruptions that generate pyroclastic flows, which are these, which you can see in the top right here. So pyroclastic flows, if you don't know what they are, they're just basically big, it's like big currents, really fast-moving currents of hot gas, ash, and rocks, and they're amongst the deadliest of volcanic hazards. But to an extent, at a certain volcano, you can kind of predict where they might go, because they generally follow the path of least resistance down the drainage channels of the volcano. And if you look at this bottom panel here, you've got a satellite image of Volcán de Fuego, and zoomed in on the bottom right there, and you can make out that there's about 5 or 6 main drainage channels in brown, that go down from all sides of the volcano. And in particular, I was interested in looking at one of the flanks on the western side, and the motivation was basically a strange path taken by this pyroclastic flow during an eruption in June 2018. So here you can see an image of this flank and this drainage channel before the eruption in 2015. And you can see that the channel and therefore where the flows are going follows a fairly simple, it goes around this curve here and then goes straight down the side of the volcano, which makes sense as following the path of least resistance. But then if you see the bottom panel here, in 2018. This is just taken after the eruption. And you can see that actually you've had a flow. You can see there's been a massive change. And what you can see is just to the north of where this channel was, where the channel in 2015 was, you've had a flow come down here and take this really sort of curvy left, right, then left turn, and then come down here. Which was really odd when we see it. We didn't really predict that this was going to happen. You wouldn't have looking at the image from 2015. So we wanted to find out basically what caused this change, and how does this change the risk for nearby villages. So to see this, we used DEMs, digital elevation models, that I talked about earlier, showing the topography before and after the eruption. To compare basically what's happened to the channels between those times. And just for a bit of context, to see what these pyroclastic flows can do to a landscape, this is before and after a pyroclastic flow in 2017. This is looking at the same channel, and I mean you can see just the complete change in the landscape. So before you had probably about a 30-meter deep channel here in the top image, and then afterwards you can see this has been totally infilled by the pyroclastic flow, and now you have just this flat deposit on top. So anyway, we looked at the changes in topography, and we found a whole bunch of changes. We found that the depth of these drainage channels changed up to about 50 meters in the 3 years that we were looking at, and that's both from getting deeper through erosion and also losing depth because of pyroclastic flows infilling them. So the next thing we did was we took the topography before the eruption and took the topography after the eruption, and we simulated the same pyroclastic flows down there to see which path they would take, see which is the path of least resistance. And you can see you've got the 2015 one here in blue, and then the 2018 one after the eruption in orange. And you can see in this white box here, you've got this more northern channel, which is inundated with the pyroclastic flow in 2018, but not in 2015. Which was a big change that we saw. And you can see there's quite a lot of villages around here, close to the volcano. So obviously, the changes in the drainages here had big knock-on effects for the potential hazard to those villages from the pyroclastic flows. So yeah, that was a really interesting case study of how dynamically the land can change around volcanoes and how that can affect the hazard. And then the second and final case study I'm going to talk about is monitoring the forming volcanoes in the East African Rift. So this is something that I'm doing at the minute as part of my PhD. So to situate where we are, we're here in the east side of Africa, where you've got the big Rift Valley, and basically down the whole east side of Africa, you've got a big long rift where basically the two sides of Africa are very slowly splitting apart. You've got two different tectonic plates there, and these rifts are associated with volcanoes. So there's almost 100 active volcanoes within the length of this rift, and millions of people live close by to these volcanoes, and almost none of these volcanoes have any sort of ground-based monitoring, and yeah, very little is known about them, at least till recently. So that makes them a really good candidate for looking at them through satellite data, um, to try and understand what's going on and if they are and how dangerous they are, basically. Um, so here we focused going back to the different techniques we can use and the different measurements we can use. We specifically were looking here at measuring ground inflation and deflation at East African volcanoes. Like I say, using the technique called INSAR, and this revealed to us that we didn't really know before, that at least 16 of these volcanoes were actively inflating or deflating, and you can see a map of them here on the right. So they're all up and down the rift. This is basically from Eritrea down through Ethiopia and into Kenya. And what do these images, satellite images, look like? Well, here's a selection of them on the right-hand side. If you remember back to earlier in the talk, I said the way to interpret these images, because they look very psychedelic and odd, but the more of these coloured fringes you see, basically the more deformation there is. I've circled basically where most of the deformation are in most of them with the black circles here. And yeah, you can see that hopefully that there's a wide range of shapes and sizes of these patterns. So in this data set, we've got ones between less than a kilometre squared to over 2,500 square kilometres. And we also see variations in how they change over time. So these two on the bottom are just plots. This is from 2015 to 2020, showing how the ground around certain volcanoes is deforming. So this one on the left is very consistently uplifting, about 5 centimeters a year, and then on the right we've got this other volcano which had a very short-lived subsidence of up to about 20 centimeters. And yeah, so the size and shape of this signal can really help us to estimate the cause of deformation. And this is because we basically think of the deformation being caused by a magma chamber below the ground at a certain surface, at a certain depth, sorry, and how deep the magma chamber is under the ground and how much it's inflating or deflating by changes the size and the shape of the signal that we see at the surface. And basically, the closer the magma is to the surface, the more likely it is to erupt. And so if we look to the bottom right here, if we have our INSAR data, our satellite image with our ground deformation signal in the middle, we can basically estimate with what size and depth of magma chamber might best fit this inflation or deflation that we see. So you can see that here, and you can see there's not much difference left over between the two of them, showing that yeah, that's a good fit. And like I say, the closer the magma is to the surface, the closer this magma chamber is, the more likely there is that there's going to be an eruption. So that was just a couple of case studies from my own work about the kind of things we can use satellite images of volcanoes for. And I thought I'd just end finally on what is the future of monitoring volcanoes from space. Well, hopefully, with any luck, we'll have more satellites, more observations, and better quality data. This is just basically something that's increasing all the time. There's more satellites being launched. And another thing that's really going to increase actually is artificial intelligence. So basically, the more data we have, um, the less basically the less images we can look through manually as scientists. So the more we need to rely on artificial intelligence to have basically a first comb through of images and find us images of interest. This is a really big expanding field at the minute. And with any luck, having more observations, better quality data will allow us as scientists to make more confident decisions about what volcanoes may do next if they're sort of in unrest or uh, doing something interesting and also quicker, which is the key point in sort of aiding decision making on the ground during a volcanic crisis. And there's also been talk of having a dedicated volcano observatory in orbit, basically having an orbital volcano observatory, so having teams of people whose sole purpose is to look at look at satellite imagery globally and identify volcanoes um, which may be looking like they might erupt soon, or just showing interesting signs, um, nonetheless. So just finally, I just wanted to leave you with some take-home messages um, from this talk. If you take four things from this talk, I hope that it's firstly, one, that many types of satellites can be used to observe volcanoes. The two, using satellites for volcano monitoring can be safer, cheaper, and more reliable than traditional ground-based equipment. Remember the pictures of the Italian volcanologists from the 1930s, for example. Thirdly, we can measure a huge variety of phenomena at volcanoes using satellites. And finally, that increasingly so, satellite data from volcanoes can be used during disasters in near real time to help save lives. And that's, I think, the great motivator for everyone working in this field. That's the kind of collective goal with working to understand these type of data and type of signals. Um, so with that, it's been a pleasure to chat to you all. Thank you all for listening.